In this last subsection on sorting, we will look at how to parallelize the sorting algorithms that we've previously studied, Quicksort and Mergesort. We start with Quicksort because that's slightly easier. There's two parts to Quicksort, as you will remember. There's the partitioning step and there's the recursive calls in the left and right subarrays. Now, the recursive calls are immediately data independent because they work on disjoint parts of the array. So you can just call those in parallel, and we will write, you can effectively write this in pseudocode as you want, but well, I'll show you one way at the very end how we can do this. So that's the easy part. Whereas the partitioning algorithm seems tough to parallelize. I want to make one further comment here. If you were to only parallelize the recursive calls, it seems like this should massively help because instead of recursing on two things, you just recurse down on one side effectively in terms of time. But the problem is that then the parallel time is entirely dominated by the first partitioning step, and that takes linear time. So the best we can hope for is to reduce time to linear. And while that's better than n log n, it's not exactly great because it leaves a lot of potential for parallelization on the table. And indeed, parallelizing it and only getting a logarithmic speedup is not usually scalable to really big inputs. So we definitely have to parallelize the partitioning step itself as well. And that seems more challenging, but we can, again, view the problem slightly differently, and then we get to something that can be parallelized. In this case, we can do it in 3 rounds. We can first do all the comparisons with the pivot element, and we can store the results. Then we can compute prefix sums of this bit vector with the previous. You see how parallel prefix sums occur here over and over again. And as a last step, we compute, we compact the subsequences of small and large elements, again with the primitive we've just seen. So in total, that is what gives you a parallel partitioning method. Let's do a quick example here, maybe. Again, okay, I want to make it really small so that doesn't eat up too much time. I'm just making this up. And let's say 5 is our pivot. So what we would do is we store a bit vector smaller, and then 3 is smaller than 5, 7 is not smaller than 5, 1 is smaller than 5, 2 is smaller than 5, 6 is not, 8 is not. And well, it might be helpful to do the same thing for the larger elements, which here is effectively just negating everything. And now we have a compaction problem like we've seen it before with S. If we compact this array, we just select the smaller ones. So just selecting those where there's a 1 in S gets us to this, and we probably want to start at the front because we want to put the pivot in between. And the other ones have a 1, so we want to put them after the pivot and put the pivot in between. That is partitioning in a way that is friendly for parallelization. And in the full glory of the code, this looks like this. I know this looks a bit intimidating, but I just wanted to spell out all the steps. There's not much complicated happening here. We have a recursive procedure parallel quicksort, which looks exactly the same as the previous one. The exception is only that here we say in parallel you call yourself recursively. That's the only difference. Other than that, it's choosing a pivot and calling the partitioning function. But the partitioning function is also parallelized now. And what it does is, well, it swaps the pivot to the last position here. That turns out to be more convenient. Then in parallel, we do the comparisons. So you compare your element against the pivot. And I use this notation. If you have a predicate, something that can be true or false, I write this square bracket, and that's just to mean 1 or 0 if the predicate is true, and 0 if it's false. So that's just a shorthand for that. And so S is smaller, L is larger. That's just the inverse. Then we do the parallel prefix sums for those two parts. Calling those in parallel is fine, but only saves a constant factor. I could have left it out as well. And now we use here that this is essentially the number of small elements. That's the starting index for the big elements. And then we have another loop in parallel where we read the old value at position I and write that value to either the so-and-so many position in the small array or in the big array, depending on whether I is smaller than the pivot or not. We could have replaced this check with SI, but we have overwritten SI in the prefix sums, so it's most convenient to just do the comparison again. Usually the comparison is fairly fast compared to the overhead that comes from the parallelization. Yeah, that's it. That code exactly realizes what I did on this example. So I don't want to comment on this much further. If you read it in more detail, you will see that this is exactly what the code does. There was a question on this that I want to show. Let's stop the poll. I'm not sure what HyperQuicksort is. It might be a parallel model using hypercube networks. So that's more of it's more a distributed model where you send messages around. Maybe you have to send me more details about this. Any other questions about the parallel quicksort? If so, then put them in and we can discuss them. And I would want to briefly discuss the analysis before we move on to Mergesort. By going through the code, you see that essentially all steps in the partitioning procedure are just constant time in parallel. The only thing that's not constant is the prefix sum computation. So that gives you a logarithmic time. And that's the time for partitioning. But we don't just do one partitioning step. We have to recurse. Now we do the recursion in parallel, but we still have to execute one recursive step after the other, finish the partitioning at the top, recurse on one side, because there's data dependencies. You have to finish partitioning at the top first before you can recurse. So we get an additional factor from the depth of the recursion tree. And remember, we talked about this, they're like binary search trees. So the expected height of this tree, or even with high probability, the height of this tree is logarithmic, which gives us a log squared time in expectation. And for the work, the partitioning call is very simple except for prefix sums. And we know how to do this with blocking. So you can reduce the amount of work also for the prefix sums to linear. And so we could essentially slash off the power of the 2 here if we want to use the blocking version. So we can achieve n log n time. The comment is below here, so I'll just leave it as it is. With the simple prefix sums, you get n log squared n work in expectation. With the work efficient prefix sum, you get expected work efficient sorting. N log n is best possible because we're still in the comparison model. You remember the lower bounds. It doesn't look like there's other questions on Quicksort for now. So let me briefly move on to Mergesort. We can parallelize Mergesort in a similar way. The recursive calls exactly the same argument. They're data independent, so you can parallelize them very easily. What's not so clear is the merging step, because again, the sequential algorithm used to get the smallest from the runs one at a time, and it seems this can't be parallelized without again formulating the problem a little differently. What we have to do is treat all the elements independently in a way. And indeed, this is possible also for merging using the following idea. The correct position for some element in one of the 2 runs. So the input to the merging procedure, if you remember, were 2 runs like this. And let's suppose we have some element x here. Now the output looks like this, a one sorted long run. And at some point we have our x. So the question is, where does this x belong? Can we somehow find out where x should go without going through all the data-dependent steps of the standard merging? And the answer is yes, because it's a sorted list. So the position of x is its rank, the number of elements that are smaller than x. And the number of elements smaller than x is the sum of 2 things. It's all those guys here and, well, all those guys that are before a certain bar where x would be if it was in the list, but it's not really there, so we don't know how many these are. But for one of the runs, we can just take the position of x, so that's easy. That's the first comment here. And for the other run, we can use binary search to find the insertion position. We just pretend we wanted to insert x into the other run, use binary search to find the position, but then don't insert it. We don't really want that. We just want to know where it would have belonged. And that gives us the rank in the other run. And then adding those 2 things up gives you the position in the output array. Again, I'm assuming here that as for standard Mergesort, we have a buffer space where we write elements to. That makes it a little easier. We have to buffer the outcomes of these binary searches. If you do this, I have to speed up and get to some other topics. I could keep on talking about sorting, but I want to keep this part, bring this part to an end now. So no detailed code for Mergesort, but what you can do is you get in parallel time, you get log n from all the binary searches, but you do them all in parallel. So for each element, you do a binary search in the other run. Everything else is just constant time in parallel time. And the depth of the recursion tree in Mergesort, again, is logarithmic. And this time, it's even worst case, because we always cut things exactly in half. So we get the same total time as for Quicksort, except that, again, here it's worst case, not only expected. The work is slightly worse. We need to do n binary searches, and each binary search needs log n steps to find the position in the other run. And that gives us an n log n work per merging step. So if you multiply that again with the depth of the recursion tree, you get to n log squared n. It doesn't seem to be easy to improve this with any very simple tricks, but it is possible to get down to linear work for merge. And the trick is to not do the binary searches for all elements, but only for some of them, which gives you a range for all the others. And then you can use a simpler method within that block. But it's a little more complicated because you cannot easily control the size of the blocks. So no details for that. Essentially just the claim here that linear work, again, is possible for Mergesort. So you can also turn parallel Mergesort into a work-efficient sorting algorithm. And again, you get the parallel time log squared, which is a really good speed up in practice. I want to finish this unit with a last comment on the theory state of the art for parallel sorting. It turns out if you try to get below this log squared n, you have to use more sophisticated algorithms. But it is possible to do it with just log n parallel time on our concurrent read exclusive write RAM model. So that's the standard model that comes closest to what we can realize in practice. These algorithms tend to have overhead in that they use very small units of work, and that's not what practical implementations like. I didn't talk a lot about how the PRAM compares to practical models of concurrency. Most programming languages give you threads that you can start. So it's some programming languages allow you to do loops in parallel, but with restrictions. Most programming languages allow you to spawn a new thread and interact with it in various ways. So there's usually some overhead attached to starting off parallel computations and then synchronizing them back so that you collect all the results. So what you really want is not two small units of work, which is also the reason why implementations like the ones in the Java library tend to use methods that are very similar to the parallel quicksort and mergesort that I've shown you, because there you can reduce the granularity of parallelization, of parallelism. But still, it's interesting that you can get rid of this log squared factor, at least in theory. And that needs interesting methods, but that's beyond the scope of this class. And yeah, that finally concludes the unit on sorting. I hope you enjoyed this part. We've done a deep dive on parallel methods and the prefix sums. And we've seen that this is the core step to solve sorting in parallel with very good parallel time and essentially optimal work. And that's the basis for parallel sorting.